Hello and welcome to Mech Designer YouTube channel. I'm going to talk today a little bit about the new features that we've introduced in release 15.1 of Mech Designer. There are two main extra functions that we've added. The first one is we've improved the library import function. Version 14 had the ability to import libraries, but it was pretty restricted. You could only ever import a library function onto a new plane. You could never import it into an existing mechanism. Well, we've changed that so that now you can, and you've got some standard library geometric shapes and mechanisms that you can import as well. We've also added a new function block for creating or helping to design crank sliders or crank mechanisms where the crank rotation is where a complete crank rotation is required, but you need to design the motion of the output of the crank. It sounds a bit complicated, and it's probably best if you listen to the video at the end, it explains it a bit more and what it's used for. So I'll start off by talking about the library import. Okay, so I'll start by demonstrating the new library feature that we've developed, library import feature. And the way to access this is if you open the input-output toolbar, which is on the extreme left-hand side of the top bar here, just click on that. Then the icon is you're looking for these little books with a little magenta arrow. You click on that, and a dialog will appear, and this includes all the library files that we've compiled in a sort of standard library. You've also got a user library, so of course you can create your own library functions, library files, which you can then repeatedly import. So for example, you might have a standard CAM design that you use, so you can save it as a library file and then repeatedly import it into various mechanisms. So how this works is you have for each of the little standard, so for example if I start with the top one, which is a crank, so if I click on that, then a little image, a little thumbnail showing me what it's going to look like when I've imported it, and a bit of a description. To load it, I just simply hit the load button. Now in this instance I've attached it to the front plane. I didn't select any plane, I didn't select anything, and so it's just gone straight onto the front plane. The front plane, and I'll just drag that across so we can see it. It's just a simple crank, and if I run it, then it of course it rotates like a crank should. Now if I move this out of the way, there's a little folder here containing all the function blocks. You can see that this one is grayed out, which is the motion design, so the motion dimension. But there is a design set here which allows you to change the parameters. So if I double click, I can't do that because I've already got this dialog open, so I'll shut the library function and open this design set, and this controls various parameters or dimensions of the crank. So I'll home it. And then, okay, I've got an initial angle here, which is this angle here, which I can control by just hitting these spin boxes. I can change the length of the crank by hitting these spin boxes, and I can change the offset position and the X and Y positions. So this gives me a little bit of control over it. So the idea of this is just really to get you started. If you're not familiar with Mech Designer, then you can very easily get a crank going, and then I can just use this, I can build on this. So for example, I can add some more geometry, say down here, and we can create a simple 4-bar mechanism like this. I just have to drag a part out there, put another part, I don't know, from here to here, and then I can use that crank to develop a 4-bar, and then I can add cams, etc., etc., as we know and love we can do it in Mech Designer. So that shows an example of a crank. Now suppose I wanted to add a little bit of geometry to this coupler. then I can do that as well. I can, if I double click on this coupler, so that'll take me into the coupler's editor, part editor, geometry editor. And now I go to I click open the library feature, then I can, maybe I want to put a curved slot on that. So I click on the curved slot, and again it shows me a little thumbnail showing what it's going to look like when it's been imported, and a bit of a description. And I hit the load button, and in it comes. And I'll close that down. And there's my geometry added, and then I can drag this around, or do various things with it. So I can dimension it. But it's geometry that's been attached to the coupler because that's the part that I was editing. And I can demonstrate that because it'll move with the coupler. And I can, I can make that into a profile. Let's make a little solid out of it. And turn solids on so they become visible. You get the planes come on as well. But there's a little solid. And there we go. We have a sausage on the coupler. So there are lots of options with the library files. If I open it again, we can see that not only have we got several geometry options, but there's some standard mechanisms which generate straight lines which you can import as well. So for example, if I create another mechanism here, I'll put it on the front plane again. Turn the solids off so the planes disappear. And then let's have a look, see what a Roberts straight line mechanism. Again, this is what it's going to look like when you import it. And then there's a bit of a description and some of the variables in the design set to control it. So I'll just load that. Let's have a look at it. Then in it comes. Turn off the library feature. And there's our Roberts mechanism. And you can see here that this line here, which is attached to the coupler, generates a straight line which moves between the two centers, grounded centers for pin joint centers, and that generates a straight line. Or we might choose to have let's try another mechanism. So if I go to the I don't know, put another mechanism on, and then we can have a look at perhaps the Chebyshev. So here we go. I'll move to look at the Chebyshev. Okay, this looks just a bit more interesting. This looks like a 6-bar. There's a bit of a description again, so I'll load that. Dismiss that, and we can have a look at cycle this one. And we can see the Chebyshev mechanism is just these two crossed links here with the coupler, and then attached to the coupler, attached to the Chebyshev mechanism is this dyad to make a 6-bar. And I think it's a translating link that. I have to talk to Kevin about. I think it's a translating link. So you can see how the library features work now, and you can attach. I could create a mechanism. So you've watched me do it. I can either directly import them onto a plane, into a mechanism that already exists, or onto a part. I think I can, if I just click on this part, for example, I can actually import another. I can import that Chebyshev directly onto the coupler of the original Chebyshev. Let's have a look, see if I can do that. So there's the Chebyshev. I'll just load it onto this part here. Oh, that's done something. I'll build that, and then yes, it looks like we've got a Chebyshev on a Chebyshev. So you can see how you can quickly build up different mechanisms using the library feature. Now you could always create library features in Mech Designer. It's very simple to create a library feature. I'll just quickly run through that. So let's go new. I'll create a new mechanism. No, I don't want to save it. Okay, just show you how to create a library feature. The first thing that you need to be aware of is we need to have a look in the the application settings, which is this blue head and shoulders icon. So we click on that, and we need to go to General, and then under General is the file options, and here are listed the directories that Mech Designer uses for example, where all the tutorials are stored, the database directory, and the user library file. So this is where you store your personal library files, or you can store your personal library files if you want to see them appear in the dialog that we've been using previously. You don't have to store them there, you can store them anywhere you like, but if you want to see them in that dialog, that's where the best place to put them. So it looks like Documents PS Motion Library. I think that directory, when you install Mech Designer, this directory will be automatically created in your Documents folder. So the way we do it, it's very simple. You just let's just create a model. So I'll just create a mechanism, put some geometry on it, a couple of lines. Say, let's do a very usual crank, maybe a crank slider for a change. How about that? Something a bit different. So, oh, no, I don't want that. So I'll just undo that. I want to attach a part to that point there, and then a motion dimension to drive it, and something make it a crank. So I'll just drive it with a linear generator or a clock, and then we'll just make a crank slider. So when I do a crank slider, if I want to create a slider joint, you just drag it over. If you drag the end of the part over a line, then it will automatically, if you click it, it will automatically create a sliding joint. And this should be a crank slider. Let's just check it is. Yes, there it is. It goes all the way around, moves back and forth. Oh, not so good. Not so good. I don't want that. So we'll just reduce this a little bit, I think. Reduce the crank length a little bit. Take it down to about, I don't know, 60, something like that. Maybe that'll work. Let's try it now. Oh yes, that's fine. Okay, not a very nice transmission angle, but nevertheless, we're going to use that as a library file. So very simple. All you do is just save it. You go to the Save As, and here you can select the LXL, not the LXL option, which I don't know what it stands for, but basically it's a library file. Click on that. And we're already in this directory, Documents PS Motion Library. That's where you want to put it if you want to see it, and we'll call it Crank Slider. Okay. Now, if we go into the sorry, I've got a bit stuck here. If we go into the library import feature, and we can see that we've got a crank slider. That we've just created that. There's no little icon. You can create your own little icons if you want an icon for your slider. Just all you have to do is, I think it's create a 24 by 24 bitmap or ping. I think it's a ping format, and call it in what you do is you just call it crank slider and then append the word 24 after it .png, and it will just automatically pick it up. And you can also create a thumbnail. I'll show you how you do the thumbnail. So what you do is, I'll shut that down. I'll just move. You don't want a huge thumbnail, so we'll just drag this over into the corner over here, and then click on the print option, and you've got save image there. So we'll just get the image about that big. Yeah, I don't want it too big. Save image, and then call it. We're in PS Motion Library, so I'll just call it crank slider. I have to get the space in. It has to be exactly the same name, and it's going to be a ping file. So crank slider, and save that. Okay, and then when I go back into the library file, when I click on it, there's the thumb. And you can create similarly if you want to put a description into what it says, you just create an RTF file, which you can create in Word, in Excel, not Excel, Microsoft Office Word. You can create an RTF file, and again call it by crank.rtf, and it'll Mech Designer will pick it up, and you'll be able to read the information about it in your user library. So that's how you can create your own library of various mechanisms, cams, gears, whatever it is you want to create, belts, whatever it is. You can put it in here, and then it's a standard setup that you can reuse and to your heart's content. It's a good idea to put to sort of. I guess you need some sort of standard way of doing this. I think it's probably a good idea to have put the function blocks in a folder, and then a design set to control important parameters that are relevant to the particular model or library file that you've created. Okay, so that sort of is all I want to say about library files. Other than these are slightly weird ones. These are just really for Camlinks. Those of you who remember Camlinks, Camlinks used to work by attaching dyads or creating dyads. I mean, Mech Designer uses the same mathematical formulation as Camlinks, intersection equations, and it constructs dyads, but it compiles joints and parts into dyads, and then solves it in the way that Camlinks does. But this is just for people who are more familiar with Camlinks, really. So you've got an XPX. So this is you can obviously attach any joint to the two ends here, and you've got a prismatic joint or a sliding joint connecting the two parts, and so that's an XP, P for prismatic, and an X. Two parts. Again, you've got the two endpoints which you can connect to a mechanism using any joint you like, and these two parts are connected with an R, so that's an XR. So you can create dyads in. It's got them here. This will form an RRP or a PRP dyad, depending on what joints you connect to the. You connect this dyad to the mechanism that you've already created. Okay, so that's it on library features. Next, I'm going to talk about I think the continuous motion crank. Okay, so yeah, we were asked by a customer to develop this function block, and we had to think about what they were saying, and we sort of agreed with them that it would be a good idea. The idea is to have a continuously rotating crank, or rather a crank that can rotate in the same direction, and yet have a developer which is connected to a mechanism, and the output of that mechanism is controlled by a motion. And as we think about it, there's certain difficulties with this particular problem. But we thought anyway, it'd be quite useful to have this function. So we developed a function block to achieve this called the continuous crank. Well, a good place to start is the crank slider mechanism that we created just now to demonstrate how to create a library function. So here we've got a crank slider, and the crank is rotating with uniform velocity because it's connected directly to a machine clock. But there are occasions where you want the output of a mechanism like this to describe a specific motion. For example, on the forward stroke of this pusher, this might be a pusher or something, and on the forward stroke you want this mechanism to follow a constant velocity, for example, in which case but you want the crank to keep rotating as well. You don't want the crank to stop and then or reciprocate back and forth, which would be a way of doing it in Mech Designer, but suboptimal, because if you've got a motor and a gearbox attached to this crank, a servo motor and gearbox, then you're going to have to decelerate not only the inertia of the that's attached to the pusher or whatever and these links, but you're also going to have to stop the motor and gearbox. So you're wasting energy, really, or the torque requirement of your motor is massively increased because you have to decelerate the motor inertia and then spin it up again. So you get away with using a much smaller motor and gearbox if you can keep the crank moving, so that the torque requirement on the motor isn't as large, and therefore the inertia of the motor can be reduced, and so the performance of the whole system can be improved massively if we can keep this crank moving continuously. Right, so the problem is, how do you do that? So we can put a motion on here. So if I put a motion on the output of this and drive, it would just change the way that we've driven this. So what can I do? I can put take this motion dimension off, and so this is the way you would normally do it. Let's suppose that we put a motion dimension now on. I need to drag this around a bit. Hang on. Let's put where will we put the motion? Let's put the motion dimension. I mean, it's a bit arbitrary. This we'll attach it to the slider. I think that'll work. So there we go. There's our slider. Oh dear, it's flipped. So we want to move that to the other direction. I think we can change this. So If I go negative here, does that do anything? Negative? No, it's negative motion. Negative base value. Bang. There we go. So I've reversed the sign of that motion dimension. Now, will it cycle? Let's find out. It's a bit of playing around. Oh, no, I need to attach. Obviously, I need to put a motion on it. So we'll get a motion, just a standard motion for now will do. So connect that up. So the motion we're using is standard motion, which I'll show you. There it is. Just a standard motion. In fact, I might as well build this back in. I'll just pop this back into. There we go. Makes it a bit clearer, doesn't it? So let's have a look and see if this cycles. I don't think it does actually. No, it's seriously broken. So I just need to offset this base a bit. Let's increase this a lot. Try that. Okay, how's that looking? So cycle that. Okay, so there we go. We're now executing a specific motion. Back and forth. So this slider is controlled by this motion here, so you can see what's going on. Okay, so where are we? It's the return, and it's in this section now, and now it advances, dwells here, and then returns and dwells again. Okay, so that's what it's doing. Now, let's suppose that's what we want it to do. So what we can do is we can add a oh yeah, sorry, I've lost the thread of what I was saying. So what we want to do is not have this rocker rocking back and forth, but we want a crank. We want it to be continuously rotating, but executing this motion. So how can we do that? Well, the way that you can do it is by adding a new function block that we've created, and it's called the continuous crank. There it is. That's the icon for it. It's a bit. We might change that icon. It's a bit similar to the design set, but we'll see. But there. So I'll pop one of those in there. And how does this work? Well, very simply, we just double click on it in the usual way to edit it, and up comes a form like this. So the first thing we need to do is select a crank. Well, I might as well select that. So I'll select that crank there, and we want a single direction. It says not create, not select. Oh, I have to click in there. That's right. So I'll click in there. So there we go. It collects it in a single direction, and I've selected a counterclockwise direction. Now, if I cycle this, we should get the crank just going round and round and round. Yeah, right. So it's not doing what it's actually a bit. It's not quite right, this, because it is actually stopping, which is what I said we don't want to do. But you'll notice that it is moving continuously round and round and round. So what we can do now, when I say it's moving continuously, it's moving in the same direction. So we can now develop our motion to keep this, to make this do what we want to do, really. Because remember, we're controlling this part here by this motion. So it's using the inverse kinematics of Mech Designer, and we develop, and this crank is executing the required motion in order for the slider to achieve this motion. So it's doing what we want it to do. So what it did was, what effectively this function block does is it knows the stroke, so it can calculate the required crank length and coupler length in order to achieve that stroke. And then what happens is, what would ordinarily happen is that it would just bounce back again. But because it knows when it's at its extreme positions, it can change the closure. And that's what the function block does. It just detects when it's at its extreme positions, and then it changes the closure. And thus you get this rotating, continuous, not continuous, it's just rotating in the same direction all the time. So that's how it works. Now, I think we'll get a better example, actually. So I'll just stop here. Okay, I've loaded the model that I think will be more suitable for demonstrating the advantages of the continuous crank. So there's a shorter crank on this one. I've reduced the stroke, and I've also modified the shape of the acceleration. The reason I've done this is that there's a problem with this, with the with the continuous crank, and it occurs at the extreme point positions of the crank. So if I move this round to what I mean by the extreme positions, there's an extreme position there. Now, when you're in an extreme position like this, instantaneously, the crank can't generate any velocity. So when we look at this motion at the extreme points, the velocity has to be 0, which it will be because it's at the extreme point. But there is another problem, and it's the acceleration. Because if the acceleration, if we sort of move this off, say 1 degree, then if the acceleration of your motion is significantly larger than what can be sensibly generated by the crank when it's in this position, then the chances are we're going to get a discontinuity. So what we have to do is flatten the acceleration a bit. Now I've used a flexible polynomial here. So what I've done is put in a non-zero jerk to try and make the extreme point, remember, is at this position here. So I should get the, let's just push this up where the extreme position is. It's at where is it at? What I'm looking at is about 310, isn't it? 310. So I'll push that to there. It's about there. So what I've done is reduce the acceleration. Is that right? Maybe is that 0? That's about right. So I've marginally reduced the acceleration at this point by putting a non-zero jerk in, and that's why you've got this sort of strangely shaped acceleration profile rather than a more uniform acceleration. It's more like a mod sine, really. Either way, this has reduced the acceleration so that there are no discontinuities required to be made by the crank motor. So if we have a look at this, we can plot this out. So we look at this motion here. This is the position of the crank. So what I've done is I've added a measurement function block to measure the angle of the crank. So that's the angle acceleration. So there's the angle. That's how the crank progresses. So it's pretty. That's the velocity. Reasonably smooth, and the acceleration. There's a bit of a spike in the acceleration at discontinuity and jerk, I guess. So now what we can do now is use the polyfit function block, which is this one here. I'll just show you how you attach that. You just take the function block, put it in here, and then we just feed into the polyfit function block the measurement. And what the polyfit will do is fit a polynomial or a series of polynomials to the motion of the crank, which is being measured by the function block. So if I open this function block, the polyfit function block, then there's the position, the velocity, and the acceleration of the crank. Now what this does is if I click on this button here, press that button, it'll fit a series of polynomials, and you can see you just about see the fitted data there. Well, it's not quite got the sharpness, so I can increase the acceleration at this point. So I can increase the tolerance. What that'll do is probably increase the number of polynomials required to fit to this shape. It depends on, if you don't want too many polynomials and you're not too worried about the accuracy of the position, then you can change the position tolerance. So let's go for a slightly higher tolerance. So I'll put 0.02% say accuracy, and then recalculate that. No change. So I'll go. Let's try a bit more drastic. 0.01%. The maximum number of polynomials that it'll use to calculate is 100. So I'll recalculate. Oh, there we go, and it sort of the acceleration matches a bit more closely. So there we have we've fitted a series of 21 polynomials to get a very good representation to extreme accuracy of the crank motion. And now I can just create a motion. If I hit that button there, then it will create the motion of the crank. And there it is. That's it's copied. It's created the motion, and there's a series of flexible polynomials in Motion Designer. So we can use that motion there and export that and to drive a servo motor, and we will achieve this motion at the output. I'll just cycle that to show you, and you can see the motion of the crank looks pretty smooth, and yet we're getting a constant velocity in the slider. Okay, I'll leave this there. Thanks very much for listening.